Understanding core DeFi protocols and core DeFi archetypes is probably the #1 way to increase your ability as a smart contract blockchain developer or as a smart contract security researcher. And so, of course, in this video today, we're going to do exactly that. We're going to master a particular popular DeFi protocol, Abracadabra Money, which is, of course, famous for creating the MIM stablecoin. And we're going to use Abracadabra Money to understand the popular DeFi archetype of CDPs, or collateralized debt positions, at a deeper level. And then once we have that understanding, a lot of other DeFi protocols will become a lot easier to understand. You'll see some commonalities and you'll be able to understand these new code bases a lot easier. So in today's video, first of all, we're going to understand at a high level what CDP protocols are, what they do, how they work. Then we're going to understand the architecture of how Abracadabra Money achieves this and the design decisions that they made. And then we're going to actually dive into the code of Abracadabra Money, and we're going to see exactly what this looks like in the actual implementation. We're going to understand the code base, how it works, and everything like that. All right, and of course, before we dive into all of that, my name is Owen, and around 2 years ago now, I founded Guardian Audits, and ever since then, we've uncovered literally hundreds of vulnerabilities in smart contract systems, and particularly in complex DeFi systems. And throughout all of those bugs and vulnerabilities uncovered, I've personally spent a couple thousand hours reading and auditing smart contracts. And my goal with all these videos, and especially this one, is to distill down everything that I've learned from those few thousand hours and give it to you so that you can ultimately absorb all of my experience that took me, at this point, 3 years now to get, and be able to condense that down, give it to you so you can become a blockchain developer, a smart contract security researcher, whatever you're looking to be, in a fraction of the time. So with that out of the way, let's dive in to this Abracadabra Money overview. All right, fantastic. You can see we are in the whiteboard of truth and justice here today, and that is because we're going to be talking about first CDPs, and then we're going to understand what is the architecture of how Abracadabra Money and implementation of a CDP protocol, what does that architecture look like, and then we're going to look at the code. We're going to see what the code looks like, and we're going to walk through that. So first of all, let's understand what is a CDP protocol, right? The CDP protocol essentially just allows anyone to come and deposit their collateral. Let's say I deposit 5 Ether as collateral, and we'll zoom in here a little bit. Let's say I deposit 5 Ether of collateral, and I want to borrow against my collateral. So I put 5 Ether in, and with a stablecoin CDP protocol, that's supposed to be Ethereum, I will be able to borrow against that a certain number of the stablecoin from the protocol. Right, so if I put in my 5 Ethereum, let's say 1 Ether is equal to, let's say, $5,000. That is the current price of Ether. I'm going to be able to borrow a certain amount of stable coins based on the value of my collateral. So I put down 5 Ether, which means I put down $25,000 of value here to borrow against. Now, I might be able to borrow maybe 20,000 stable coins. So in the case of Abracadabra Money, that is MIM, which is the stablecoin for their CDP protocol. Now, we'll notice one key thing here is that I am required to deposit more collateral, more value of my collateral than the amount of stablecoins that I'm able to borrow. And the reason for this is we always want to be able to hold this core invariant for every one stablecoin in circulation. So for every one MIM, in the case of Magic Internet Money, in the case of Abracadabra Money, there should always be at least, so greater than or equal to $1 of debt backing that MIM, that stablecoin that was issued. And why is this important? Well, this is important because this is how we hold the peg, right? And in a CDP protocol, I like to say the stablecoin is worth $1 to somebody, right? For this thing to hold a peg, it's got to be worth $1 to somebody, right? as long as it's worth $1 to somebody, that person will always take the advantage to buy this thing if it drops to, let's say, 90 cents. Well, if it's worth $1 to somebody, they'll always buy it at 90 cents and they'll redeem it for $1, right? So who is the somebody that the stablecoin is worth $1 to? It's the people who have borrowed that stablecoin and need to repay their debt, right? So if I'm this person who has borrowed 20,000 MIM against my $25,000 of value, and I have to repay that loan to unlock that and be able to withdraw that, then of course, I'd love to buy my $1 units of debt at 90 cents on the dollar and be able to repay that 20,000 MIM debt while only spending $18,000 to do so. So this is exactly how these stablecoin CDP protocols maintain their peg. Now, of course, we need to always maintain then that there's at least, a good amount more value of collateral deposited for all of these MIM borrowed, right? So that's where we have this difference between, okay, I've put down $25,000. Now maybe the maximum I'm allowed to borrow against that is $20,000 of MIM, or 20,000 MIM, since the system is essentially treating one MIM as $1 of debt. So you're not able to borrow all the way up to exactly 1-for-1. If I put 25,000 in, I can borrow 25,000 because, as we know in crypto, your collateral, the price, the value of your collateral could be quite volatile, right? So if this is Ether, if I've deposited my 5 Ether, that could very easily go down to $24,500 of value. And then all of a sudden, my collateral is worth less than what I've borrowed. So I'll just walk away with what I borrowed, leave you with my collateral, and then the system has bad debt. It is an insolvent position that I've opened. So exactly to prevent this, what we do is we require that you put more collateral than the value that you borrowed. And I can't borrow any more of this. If I want to borrow more, I've got to provide even more collateral and then go like that. And so this is formalized in what's normally referred to as an LTV ratio, or a loan to value ratio. So what does this mean? This means for any particular type of collateral, let's say for wrapped ETH or something that we provide as collateral, there's a defined amount. So if we provide $1 of wrapped Ether as collateral, I might only be able to borrow 70 cents of MIM, or 0.7 MIM, right, for that collateral. And that would be a 70% LTV ratio, right? So for every $1 of value, I'm able to have 70 cents of a loan in MIM that I'm able to take against that. If I ever go below that ratio, so maybe for every 70 cents of MIM borrowed, I have 0.98, so 98 cents of collateral, then this position is liquidatable, right? We want to liquidate, we want to close this position before it gets even more unhealthy. And ultimately what we're looking to avoid is a situation where we're at something like 68 cents versus 70 cents borrowed, in which case the amount borrowed is literally worth more than the amount we provided. We just walk away with the amount borrowed, right? And the position takes on that delta of bad debt. So we want to have that cushion room. We liquidate somebody as soon as they go underneath that 70% LTV ratio. We force close their position. We take an extra liquidation fee from them, and then their borrow has been repaid and the system can move on. So that is how a CDP protocol works at a high level. Let's now just quickly have a look at the architecture of what Abracadabra money and the Abracadabra money system is, right? So to achieve this, there are two contracts here, two main contracts. We've got a cauldron, which is the entry point for users. This is the contract that users are going to interact with. And then we have a degen box, otherwise, might be called the bento box, because this was the original, what the original contract was called, and then they licensed it, and they are now calling it the degen box. So we'll put the degen box. And this is where all of the actual accounting and all of the actual funds for the collateral and everything is actually held in this contract. And only the cauldron is allowed to go and talk to the degen box, call the important accounting functions on the degen box contract, and the users, of course, interact with the cauldron. So what will happen is we'll see the users come to the cauldron. You can call a deposit collateral function on the cauldron contract, and then the cauldron will come and it will send those collateral tokens to the degen box. So we'll deposit into the degen box and we'll get some collateral token shares from the degen box. And the reason we have these shares per collateral tokens is because the degen box, it can actually take the collateral that's sitting in the degen box and it can go and it can put them to work in another strategy contract over here. And that can actually earn yield on the collateral while it's sitting in positions, right? So literally you can put in collateral and your collateral can be deployed in a strategy making some yield while you have some amount borrowed against it. So, and that could be even used to pay down the debt with that yield as you have your position open. Okay, but mainly what we're going to be focusing on is just the interactions here between the cauldron and the degen box. So to be clear, the degen box holds the collateral tokens unless they've been deployed in a strategy, but we won't pay any attention to the strategy details in this overview. We're going to focus on the core parts. So we're going to say that the degen box holds the collateral tokens and the cauldron will get the collateral shares from the degen box. So when you deposit collateral tokens into the degen box, you are issued collateral shares from the degen box, right? So the cauldron deposits collateral to the degen box gives collateral shares to the cauldron. That's how it's tracked, how much of this collateral has been deposited through this cauldron. And then the cauldron itself has the user per user basis accounting for which user deposited how much collateral, which user has borrowed however much amount of MIM, and are they solvent, are they liquidatable, everything like that. And we'll see what all of that stuff looks like in just a second. Now, one final interesting detail here is that on every borrow amount, so when I go and I open a position, I borrow some MIM, on every borrow amount, interest is accrued per second. So when I go and I take a loan from the bank, there's going to be some interest rate, right? Otherwise, it's just not economically feasible to offer zero interest loans unless you're the US government. But on every borrow amount in the Abracadabra money system, there's going to be some interest accrued per second. And this interest must be paid back in the borrowed stablecoin. So the interest accrues in MIM itself. And they have an interesting way of accounting for this and, sort of managing this in the code that we will dig into in just a second. Okay, so now we are going to dive into the code. We're going to see what this actually looks like in practice. And first of all, we're going to walk through the user calling deposit collateral. So we're going to call the deposit collateral function, which is on the cauldron here. And we're going to follow the collateral. We're going to see it go into the degen box. We're going to see the shares being issued to the cauldron, and we're going to see the user getting that balance recorded in the cauldron of saying this user has deposited this collateral and now they may borrow against it, right? And then we'll move on to actually borrowing and go from there. So here we are in the cauldron v4 contract. Let us scroll down. And what I'm going to do is I'm actually going to minimize everything just so we don't get overwhelmed with a ton of code. And we can see a deposit collateral function. We're going to find it. So we'll go function deposit right here, add collateral. So this function is called add collateral. So right here, we can see here is all the logic for adding collateral. So we have this idea of collateral shares that is tracked in this cauldron, right? So the cauldron is tracking the per user basis, which user has which share of collateral. And then the degen box is just getting all the collateral that all of the users have deposited, right? So here's what's happening. User collateral share for the 2 that we're choosing to deposit this collateral for gets added this share amount. So when we talk about share amounts, this has to do, for collateral, this share amount has to do with the fact that we are deploying stuff into a strategy in the degen box, means that if I deposit some collateral at t equals 0 into the degen box, I might get 1 share. So 1 collateral equals 1 share. I'm just going to type this out. 1 share. Okay. And this is at t equals 0, right? So at time equals 0, 1 collateral equals 1 share. Now, if we're able to deploy stuff into a strategy, that means that the collateral balance in the degen box will increase over time. If it's a good strategy, it'll be making interest, right? So if we go and deploy this into Aave or, some protocol and lend it out and earn interest on it, we'll get more collateral back. So let's say at t equals 10 here, my 1 share might be equal to, let's say, 1.3 tokens of collateral. So this is literally the accounting for when we have a strategy and it's actually accruing interest in the strategy, right? So that is why we issue shares, and we're accounting with shares here for adding collateral rather than a straight collateral amount. So we increment the user's collateral shares, and then we're increasing the total collateral share, right? So if we added some shares to this, now the new total collateral share can increase. We go into add tokens here, and we're not going to look at skim for this case, but usually if you're just depositing straight into this, you're going to come into this else case here. And what you'll do is you'll transfer from the message.sender to this address, this share amount. So what users will have to do is they come here, they deposit for the degen box. So the user will deposit directly, and we'll see actually in a second they have a cook function to automatically handle all of these actions together. User deposits into the degen box a collateral amount, so an amount of actual collateral tokens. They get the collateral shares. So user gets collateral shares because they've deposited collateral into the degen box. And then we're going to call bentobox.transfer from the message sender, so from the user to this cauldron. So if we go here and we find the function transfer, here's the transfer function on the degen box. So we can see we're changing the balance of from the token. So the token in our case is going to be wrapped ether, let's say, is the collateral that we're depositing. It will take it from the user, subtract it from the user, a share amount. So remember, this balance of is a share amount, not an actual collateral token amount. These are shares that we're tracking with balance of, and send it to the to address. So we're changing this balance of mapping. This is the source of truth for shares in the degen box, and we're sending the shares in that balance of mapping to be accounted for the Cauldron v4 contract. So this is exactly how we get the collateral from the user to be allocated to this Cauldron contract, and then ultimately the user's collateral is tracked here in this mapping, in the user collateral share mapping, and that is how we keep track of whose collateral is whose, etc., etc. And then there's a hook for after add collateral. There's nothing in this hook in this base contract, but contracts inheriting from the Cauldron v4 might use it for something. So that is exactly how collateral gets into the system. Let's see how collateral can get out of the system. Okay, well, we can see exactly here a remove collateral function. Now we'll see really quickly accrue is called, and this is exactly how interest fees are charged, but we won't get into that just now. Now we go into remove collateral, and we can see that the user collateral share mapping gets subtracted by the share amount that's being removed. And then really we just reduce the total collateral share for this Cauldron contract because that's what we're removing. And then there's this after hook. And then finally we have a bentobox.transfer. We transfer the wrapped ether, our collateral, from the Cauldron. So the shares, they belong to the Cauldron. Remember, when we call bentobox.transfer, we're transferring shares for the collateral token. The shares can be redeemed for the collateral token, transferring from the Cauldron to the to address, right? So when we were depositing, we transferred the shares in the bento box from the user to the Cauldron. Now we're withdrawing, we transfer the shares in the bento box or the degen box from the Cauldron to the user, right? So we just do the inverse of when we got into the system. Okay, and here we'll see the cook function that sort of automates the a lot of different things that could happen. You can do this in a single transaction by passing a list of actions. You can handle the depositing into the bento box and then calling the deposit function on the cauldron to be able to synchronously in a single function call do the deposit, which we just saw has 2 steps to it. So first of all, what you would do is you would want to call the bento deposit. So we can see here there's an action bento deposit. We would want to supply one of those actions, and then we can call the underscore bento deposit, which will just go ahead and, first of all, decode the data that you provided, then come in here, grab the amount and the share here, and then essentially just call deposit on the bento box, right? And you can configure if you want there to be a value here, if you want there to be an amount, or you want to specify a share, you can do either of those. But let's have a look at the deposit on the degen box here. All right, so here we've got deposit. This is what will be called when we want to first get our collateral into the entire system so that it can then be transferred to the cauldron. And usually what you're going to do is you're going to specify an amount and you're going to leave share as 0. And so what will happen is then they will calculate based on the current exchange rate that we discussed. One share might equal 1.3 collateral tokens. It might equal 1.7 collateral tokens. It could equal 5 collateral tokens, depending on whatever that exchange rate is at this point in time, because it changes with time if things are deployed in a strategy. We're going to calculate, okay, this is how many shares should be minted to you. And then we're going to actually increase your balance for the shares of this token you're depositing by adding that share. And then we'll see the base and elastic. This is how they're tracking this conversion between shares and collateral token amounts. So the base amount, I like to sort of visualize it like this, like if there were to be a base that is just, here's like a filled in circle. This is the shared amounts. I don't know why I think about it like this, but I think of it where we've got some circle that's filled in here. This is what I think of as the base amount, and this is the share amount that is static. It does not change. And then we have this area around it, right? This is the elastic part, the part that can grow and change and bounce, right? I think an even better way to do this is with a circle like this. So we can see like the elastic amount, it can grow and shrink. And usually what will happen is, so you have this shares amount that is fixed. That's the black circle in the middle, and it's not the greatest circle. But as the rewards from the strategy grow, then the elastic amount gets bigger and bigger and bigger, right? And this is where the conversion ratio grows, right? Because when we started, when we had this circle real small, it might even be like, well, originally starting out, it will be 1 share equals 1 collateral, right? 1 collateral token. And then the elastic supply grows and grows until it's like, okay, 1 share equals 2 collateral for this elastic supply, right? So that's exactly how they're tracking this, right? And so when you deposit, you're going to add at the same ratio. So you got a certain amount of shares, you got a certain amount of actual collateral amount that you deposited. They're just adding these to those ratios. It's not changing the ratio between the size of the base amount and the size of the elastic amount. You're just adding more at that existing ratio. But what happens when you accrue rewards, that's when the elastic gets bigger, but the base will stay the same. And that's where the ratio changes. So that's just how I like to visualize that. And then finally, they're just actually getting the tokens from you and safe transferring from you to the degen box the amount that you put in, right? So that is how you get your actual collateral ERC20 tokens into the system. You get your collateral shares tracked with the balance of mapping. And then after we've called that action bento deposit, the second action that you have in the list that's provided to the cook function is this action add collateral, which we'll call the add collateral function, which will do what we just went through, right? It will take those shares that you just got, transfer them to the cauldron. Boom, now you have user collateral share tracked in the cauldron. You're ready to borrow against it. So let's look at the function borrow. All right, right here we can hop into underscore borrow. We can see the important things that are happening here is I'm first of all providing an amount. We're calculating a fee. It's just a hard borrowing fee. And then we're adding to the total borrow here, right? So incrementing the total amount borrowed on the contract, validating it against a cap. And then importantly, right here, we're tracking the user borrow part, right? We're adding the part. So this is, again, the part is like a share amount, right? The part is this, the black circle in here, and the amount for every part is the elastic part, right? So we have this same concept happening here where we have a part and we have an amount. And the reason we have that is because this is how the interest is charged, right? When we convert from initially, when t equals 0, there will be no interest charged, right? And for every borrow part, that is just equal to 1 mim. But over time, the elastic part of this grows. And now for every 1 mim that I initially borrowed, I might owe 1.2 mim to pay back, and that is interest being charged. And so we're tracking here the static borrow amount that a user has borrowed. And later on when we have to repay, you'll see how we have to actually convert to the elastic amount, and we've got to repay the elastic amount, which includes interest. Okay, then finally, this is where you actually get your stuff borrowed, is we calculate Magic Internet Money shares from the amount, and we use the bento box to transfer those MIM shares to the to address, and they come from the Cauldron contract. So by default, when we deploy the system, the Cauldron is going to be allocated a certain amount of MIM shares in the degen box so that it's able to lend those out, right? And that's what this comment is saying here is, as long as there are tokens on this contract in the bento box balance, then you can mint, and this enables limiting borrows, right? So if there was a limited amount, well, there is a limited amount of bento box balance for MIM for this Cauldron, that means you can't borrow any more than that, right? So that's where the limiting comes in. So let's have a look at repay, and we'll see exactly where the interest fees are charged here. Okay, so in the repay function, we'll see that, first of all, in the actual function, we will accrue, right? And let's now see quickly just what does accrue do. Accrue will just see how much time has elapsed, and then essentially it will take that amount of time elapsed. It will calculate, here's how much interest accrued over that period of time, and then we're going to add that interest that should have accrued to the elastic amount. So exactly in this function, what's happening is, this is where the outer circle here is expanding, right? We're expanding the elastic supply. We're making this bigger and bigger as time goes on, and we're changing the conversion rate from the share amount to the elastic amount, making that conversion bigger. And so ultimately, this means that when we repay, as time goes on, we're going to have to pay back more and more amount, which is an elastic amount, which is an amount of actual MIM that must be repaid. So here we call this total borrow.sub function. This will actually go and use the boring rebase library, and we've got the sub function right here. We'll make that a little bit bigger. So here's the sub function, and we can see what this does is it will calculate the elastic. So we call to elastic here, which this function you can see quickly just does a conversion between the elastic equals the base times, whatever base amount. So we're converting a base amount to, whatever the ratio is of elastic to base. So we're converting base to elastic, and that is ultimately the elastic is what gets returned here. So when we sub, we actually do two things with this function. We actually sub this amount from the total, and we convert and return the base amount supplied to the elastic amount, right? So here, this is where we put in the part, which is tracking the shares that were originally borrowed, converting that to an elastic amount, right? Which is the frontier here of our circle. That's the elastic amount. And this is the amount that actually has to be paid back when we calculate, okay, now here are the shares we need to deposit on the bento box, and we transfer this share amount from the message.sender to this Cauldron, right? So that is exactly where the borrow has been repaid. And it's a little bit confusing because there's, the share logic for the degen box itself, but then there's also the rebase and elastic logic for the total borrow and the interest that's accrued on that. But both of those use the same aspect of an increasing elastic supply. Now, finally, what do liquidations look like here in the system? So if we go and we look at the function liquidate, we'll see that anybody can call this function. Anybody can liquidate anybody who is liquidatable, and you can provide a list of users to liquidate. And what this function will do is it will loop through all of these users. And really importantly, what will happen here is we'll check if if they're not solvent, or if they are basically liquidatable, then we'll go ahead and we'll require that the liquidator pays back their borrow amount. So what we're doing here is we are just computing the amount of borrow amount that should be paid back to close out their position and get everything closed so that the protocol can remain solvent. And then we're also summating the collateral share here that corresponds to the amount that should be borrowed. And that is what the amount that the liquidator will get, right? So they will pay back the borrow. They will also get the portion of collateral that corresponds to that borrowed amount that they paid back. And they're going to get a liquidation multiplier. So, something like 1.06% or 1.06x, 1.07x. So they'll get an extra 6% or something like this on top of that collateral amount to actually be able to get some incentive to cause this liquidation to happen. And so after we summate all of the collateral amounts and the borrowed amounts that should be settled here from all of the users who are liquidated, we're going to make the necessary storage changes for the total borrow and the total collateral share. And then they actually distribute a certain amount of that liquidation fee, that liquidation bonus gets distributed to the SPEL holders, the people who are staking their SPEL tokens, which is the governance token you can think of for this protocol. And then finally, what will happen is the collateral share here will get transferred from this address to whoever the liquidator supplies to be transferred to. So they'll get the collateral before they actually have to transfer in the owed borrow share, right? Before they have to pay back the MIM that was borrowed by all of these people, they will get the collateral that these people had. So here what you'll be able to do is, if you provide a swapper address, you can get the collateral, swap it for the required MIM, and pay back the MIM that way. And then the idea is that a little sliver of collateral will be left over that you didn't need to pay back the MIM, and that is your profit for just calling this function and making the swap and paying back the debt and closing out those positions, right? So that's the incentive for people to call this liquidate function. So one final detail here, which is an important detail of this, is deciding when is a position liquidatable, right? And for that, we need to look at this is solvent function. Now, this function essentially just decides, when we breach this barrier of, okay, you're at the 70% LTV ratio. That's where we're going to say, if you go below the 70% loan to value, that's when we're going to liquidate you, right? And it's technically a misnomer to call this is solvent, because you can be at 0.99 of, 99 cents of collateral for every 70 cents of borrowed debt. Technically, you are still solvent there. You have more collateral value than you've borrowed. But this function here will say it will return false because it's below the LTV ratio. But that's exactly why we have the LTV ratio, is to never allow positions to become insolvent where they literally don't have enough collateral to pay their debts. This would be better named is liquidatable, right? So it's not necessarily is solvent. It is not liquidatable, I suppose. But case aside, what we're doing here is we're just getting the user's borrowed part. We're comparing that to the collateral share. We're converting the collateral to an amount, right? So in the degen box, we need to make the conversion between collateral shares to actual collateral tokens. Then we need to multiply that through and get the actual dollar value of those collateral tokens, which is what we're doing here. And then compare this to the value of the borrow part, right? So we can see in here, we are using the exchange, the collateralization rate. The collateralization rate here, that is exactly what is denoting what the LTV is for this configured cauldron. So every cauldron will accept one type of collateral, and it will have a configured collateralization rate for that. And, for example, if this cauldron was taking wrapped ether as its collateral token, then the collateralization rate might be 0.7 like we've denoted here, or it will be, 7 with 4 zeros, right? Because it's going to be divided by 1E5. So if you go below that threshold, then this will return false. If you're above that threshold, then this will return true, and you will be solvent. You will be not liquidatable, and then you cannot be liquidated with the liquidate function. If you go below, then you can be liquidated. So that is everything to the Abracadabra Money protocol. So I hope you enjoyed that overview. I hope it was eye-opening, and perhaps you learned a few things about, just interesting ways of accounting for fees. I think this rebase and elastic idea is pretty cool. And hopefully you can translate some of these to other DeFi protocols that you look at and be able to understand DeFi code bases a lot easier. So with that out of the way, of course, if you really are interested in this DeFi stuff, in this Web3 security stuff, then of course you can join us in the community at lab.guardianaudits.com. We have a completely free community where you can connect with other security researchers, blockchain developers from across the world, and ask any questions and share the stuff that you're working on and the stuff that you're looking into, and even connect with others to work on that and team up, join contests, build projects, stuff like this. And of course, last but not least, if you are really interested in this Web3 security stuff and you want to make the transition and be able to become a skilled security researcher, even a senior smart contract auditor in a matter of months, and you're looking for a more hands-on approach to get there and not have to, spend potentially a couple of years like myself to get to that point, then of course you can go down in the description below. I've got a 6-step guide there for you where we can figure out how to get you from where you are right now to where you want to be as a senior smart contract auditor in 6 months. So if that's something you are interested in, you can get the guide down below. With that being said, I will see you in the next one.